In the earlier class, I have talked about that angle of friction is equal to the angle of the force. Now, let's in this class talk about the Newton's law of motion. I am starting with the first law of motion. Everybody remains in the state of rest or the uniform motion in a straight line unless it is compelled by some external force to change that state. Now the second law is the rate of change of linear momentum of a body is directly proportional to the applied force, and the change takes place in the direction of the applied force. That is dp by dt equals to f. Here this is the momentum vector p vector, and dp by dt represents the rate of change of momentum vector with respect to time, and which is equal to force vector applied force. It gives the measurement of force. Now consider a body of mass m moving with a velocity v vector. Its momentum is given by p vector equals to m into v vector. Now differentiating with respect to time both sides, we get dp by dt equals to d by dt m into v vector, because m is constant, so it comes out of the differentiation, equals to m dv by dt, or dp by dt equals to m and dv by dt, which is equal to the acceleration, so m into a vector. This is equation 1, and according to second law we know that the rate of change of momentum is equal to the applied force, so dp by dt equals to f vector, equation 2, and so from 1 and 2 we get f equals to ma vector. That is, force is equal to the mass into acceleration. Here F represents the applied force on the body or particle, m is the mass of particle or body, and a is the acceleration acting on the body or particle. And this is the resultant force. This law is applicable for single particle or single body system. It means that if there is a many particle system, then that many particle system will be considered at a single point, which is the center of mass, and then we apply the force, use this force for this condition. The force F vector in the law stands for the net external force. Any internal force in the system, any internal force in the system is not to be included in a F vector. And now the unit of force is Newton, represented by capital N, and 1 Newton is equal to 1 kilogram into 1 meter per second square, or equals to 1 kg meter per second square. Now its gravitational unit is kilogram weight. It is also called 1 Newton is also called a kilogram weight, or kilogram force, kgf is, it is also called kilogram force. 1 kg weight equals to 1 kgf equals to 1 kg into 9.8 meter per second square, or equals to 9.8 kg meter per second square, equals to 9.8 Newton. So 1 kg weight is equal to 9.8 Newton, or 1 kg force equal to 9.8 Newton. Third law, to every action there is always an equal and opposite reaction. Action and reaction act on two different bodies. This is the condition. Now, working with Newton's law, let us see how Newton's law can be used in solving the different types of situational and problem. If a body or the system is in rest or moving with constant velocity, then total force, that is net force on that body, is equal to 0, that is F net equals to 0, and this gives sigma F F factor equal to 0. This implies sigma Fx I cap plus sigma Fy j cap plus sigma Fz k cap equals to 0. Resolving force into component form. So in component form we get sigma fx equals to 0, sigma fy equals to 0, or sigma fz is equal to 0, and thus this formula comes from the first law. That is, this means that if body is in rest or moving with constant velocity, then all force acting on the body in x direction will be 0, all force acting on the body in y direction will be 0, and all force acting on the body in z along z axis will be 0. Here the situation is shown. For example, let a body of mass m is placed on a table and it is in rest. Now see, if we draw the free body diagram, so this will be the free body diagram, that is n is working in the upward direction and weight is working in the downward direction. If we take one direction as positive, then another direction will be negative. That is, upward direction as positive, then downward direction will be negative. So and it is along y direction, so sigma fy will be 0. Now n is in upward direction, positive y axis, so n is positive and a plus, and mg is in downward direction, that is negative, so we have written it minus mg or equals to 0, so n will be equal to mg. So n will be, or you can directly write, that is because this body is in rest, so in this direction net force is 0, and it will be 0 only when this force is equal to this force, so n will be equal to mg. Now another example is shown here. Find the tension in the string and contact force if the mass of the sphere is m. Here a situation is shown. A spherical body is hanged with the help of a string, and the body have mass m. Then we have to find the tension in the string, and this angle is theta and the length of the string is given L. Now to solve this problem we have to draw the free body diagram firstly, because here the contact force will be acting in this direction, so we are showing here. We have put this body on the coordinate axis now, and seeing the different force acting on this. First see, there will be a tension on this body in upward direction, this is shown here T. Weight of the body will be acting in the vertically downward direction, which is mg, and a normal reaction due to this surface on this body will be in this direction, this is shown n. Now we can take the component of tension in vertical direction, that is y direction, and in this x direction, because this is theta, then in this direction t will be t cos theta, and this direction will be t sin theta, and mg in this direction. Now for the body is in equilibrium, that is not moving, so all forces in this direction along x-axis must be 0, so sigma fx equals to 0. Now is if we take this direction as positive, then this direction will be negative, so n plus minus of t sin theta equals to 0, which gives n minus t sin theta equals to 0. And similarly for vertical direction, that is y direction, sigma fy must be 0, so t cos theta, this is because it is positive and this will be negative, so t cos theta minus mg equals to 0. And again from the geometry of the figure, cos theta will be root under L, because this will be equal to the radius r, and this is the hypotenuse. We consider this as a triangle, right angle triangle, then cos theta will be under root L square minus r square divided by A. So then different calculation can be uh, done, and now the third example. Find the maximum value of m so that the system remains in equilibrium. This is shown in the figure, a situation, and a body of mass m is placed on the another body of mass capital M, and these two bodies placed on the a surface in which coefficient of friction is b, and it is hanged from at point O with a string of a mass m naught, and this is angle theta. Then we have to find the maximum value of m, that is this maximum value, so that the whole system remains in equilibrium, that is in rest. that is not in moving condition. So we can solve this problem by drawing FBD. Now first we draw the FBD of mass m. So let's see the here mass m have FBD because it will be acting on by the weight of the body will be in vertical direction and normal reaction due to this mass will be in upward direction, which is n we have written. Then FBD of mass m will be n is in upward direction and in direction. So for this body sigma y is equal to 0 and n equals to mg. Now consider the FBD of m. And in this this body, because there is no force acting in this direction, only vertical force is acting, so we have not shown horizontal force here. Now for FBD of m, it is second body. um, this is the situation of second body. Let's see, this is the situation, here is it is the situation. And so there will be a tension in this string which will be pulling this body in this direction. Let's consider that tension is T, and because here friction force is also acting, so there will be a friction force acting on this in this direction. That will be a static friction force. Okay, and there will be a normal reaction due to this body in the downward direction, which will be equal to the n, and again normal reaction due to this surface will be in upward direction. Let that will be uh, r or n dash. So this is the shown in the figure. The FBD of m, the n is in mg in this direction, t is in direction, fs is in this, n dash is in upward direction. Now we know that sigma fs equals to 0. So t minus fs equals to 0. This gives t equals to fs, equation 2. Again we know that fs equals to mu into n dash, where n dash will be m plus m into g. Now sigma fy equals to 0. This gives n dash minus n plus mg equals to 0. This implies n dash equals to n plus mg, or we put the value of n mg, so m plus m into g. This is question 3. Now n dash have been calculated, m plus m into g. Now FBD of point O, we will draw the point, then T dash will be a tension in the string will be acting in this, which is T dash, and in this direction this will be in T. Let's consider this point here. A tension will be in this direction, which is called T dash, because this is another string, and a tension will be in this direction, and another tension will be in this direction, and also because it is a massless point, so there will be no weight. So FBD of point O will be like this: T dash, T and T double dash. Means that only here tension in strings are acting. Now take the component of T dash, to T dash cos theta, T dash sin theta, and this is T double. From this sigma fx is equal to 0. This gives T dash cos theta minus T equal to 0. This implies T dash cos theta equals 2, equation 4. Again sigma y equals to 0. T dash sin theta minus T double dash equals to 0. This gives T dash sin theta T double dash. Now draw the FBD of mass m naught, and here is the mass of m naught. Hello. Let's see. It is mass m naught. There will be tension in it upward and weight in downward direction. So here the body of the shown that T dash T double dash in upward tension and weight in this direction. Sigma y equals to 0. So T double dash minus m naught g equals to 0. This gives T double dash equal to m naught g. So now Dividing equation 5 with 4, we get tan theta equals to t double dash by t equal to m naught g by t. This implies tan theta m naught g by t equals to fs, and we have calculated t equals to fs from equation 2, and fs has value this, and from a, so m naught g by mu into m plus m into g equals to m naught by mu into m plus m, because g had penciled. This implies m plus m equals to m naught by mu into tan theta, hence m equals to m naught by mu tan theta minus m. This will be the, so this is the value of mass calculated. Again, see next problem. T1 and T2 determined in the given figure T1 and T2. Here it is clamped, and the tension in this string is T2 and tension in this string is T1, and it is a 4 kg weight, 4 kg mass is hanged. So we can draw the free body diagram of this point, and then solve the problem. Here this is shown. First we have draw the free body diagram this point. In this, there is two problem. One problem is this, and another problem is this. So we will solve with these two problem one by one. Now in the first problem, we see that T is acting in this direction will be T1. So we take two components, and this is 60 degrees. So this will be T1 cos 60 and this will be T1 sin 30. And in this direction there is T2 tension, and on this body there, let us consider the tension is T. Then on this body there will be a tension in upward direction and weight in this onward. Now for equilibrium of point O, sigma fx equal to 0, this gives T1 cos 60 minus T2. This implies T2 equals to T1 cos 60, and sigma Fy equals to 0. Sigma Fy equals to 0. This gives T1 sin 60 equals to T1 sin 20 minus sin 60 minus T equals to 0, and this implies T1 sin 60 equals to T. Now for the equilibrium of the body, sigma Fy equals to 0, so T minus 4 into weight, 4 into 9.8 equals to 0. This gives T equal to 4 into 9.8, equation 3. Hence T1 sin 60 is equal to T 39.2. So we can get T1 equal to like this, 45.26 Newton answer. And from 1, T2 equals to T1 cos 60. So we can solve 45.26 into 1 by T, or 22.60. Similarly, the second problem can be solved. Now next one we talk about Lami's theorem. If an object O is in equilibrium under three congruent forces F1 vector, F2 vector and F3 vector as shown in the figure, that is a object O is at this place and these are, and object is in equilibrium, and there are three forces acting on this body, F1, F2 and F3. Three forces are in same plane, and this angle is alpha, this angle is beta, and this angle is gamma. Then we have, that is F1 by sine alpha. We have to take that, if we take this force, then the angle will be in front of this force, that is this. So F1 by sine alpha equals to F2 by sine beta, F2 by sine beta, and F3 by sine gamma equals, these are equal. For example, if we consider T1, T2 and T3, and this is a condition where this point is in equilibrium, then we can directly write T1 by sine 150 equals to W by sine 90 equals to T2 by sine 120. So from Lami's theorem we can write W by sine 90 equals to T2 by sine 120 equals to T1 by sine 150. Hence T2 will be equal to W by sin 90 to sin 120, W sin 91 on sin 90 plus 30 equals to W cos 30 root 3 by 2 into W, and we have the value of W equal to 10 Newton, the root 3 by 2 into 10 equals to 5 root 3 Newton. Similarly, we can calculate T1 equal to W by sin 90 into sin 150, W into cos 60, or equals to W by 2 equal to 10 by 2 equal to 5 Newton answer. So this is the application of Lami's theorem. Again, see another example. If find a mode of F1 and F2, point O is in equilibrium as shown in the figure. Find mode of F1 and F2. Point O is in equilibrium. Here the situation three forces are acting. One force is in this direction, another force is in this direction, another force is in this direction, and another force is in this direction. So this can be solved direct because point O is in equilibrium and free body diagram has been drawn. We take the component of this force, one will be in this direction, one will be in this direction, and again this component of this force, one will be in this direction, one will be in this direction. Here it is shown, that is when we take the component, that is here is F1 and this is 4 Newton, so 4 Newton cos 30 will be in this direction and 4 Newton sin 30 will be in this direction, cos 30 will be in this, and 4 Newton cos sin 30 will be in, or cos 60 will be in this direction. Similarly, F2 sin cos 30 in this direction and F2 cos 30 in this direction, or F2 sin 30 in this direction. Now for sigma fx equal to 0, so 4 cos 60 plus 8 minus F2 sin cos 30 equals to 0. This gives the 2 equal to 4 cos 60 plus 8 divided by cos 30, 4 into cos 60 1 by 2 plus 8, and cos 30 equal to root 3 by 2 equals to 10 into 2 by root 3 and 20 root 3 Newton. Again, if we take sigma fy equals to 0, then f1 plus 4 cos 30 minus f2 sin 30 will be equal to 0. This gives f1 equal to f2 sin 30 minus 4 cos 30. Put the value f2 equal to 20 by root 3 into sin 30 1 by 2 minus 4 into cos 30 root 3 by 2, and solving 20 by 2 root 3 minus 2 root 3 equal to 10 by root 3 minus 2 root 3. 10 minus 2 into 3 by root 3 equals to 4 by root 3 answer. So we can solve a problem, different problem by using the equilibrium condition of the force.